Let's look at limits of trigonometric functions. Here, if you look at it that way, we have this semicircle and we have arc AC. You can see we have arc AC. We have two triangles here. We have triangle OAC and triangle OAB. Similarly, we also have a sector, and that is sector OAC. All right. So let's see. What do you want to learn here? Let's stay to the end of the video. Now, if you observe, from O to A and O to C represent the radius of this semicircle. So therefore, I'll be writing the radius here. So this represents the radius, this represents what? The radius. So these two are radii. So OA equal to what? OC, they are what? Radii. Nice. Because it runs from the center to the circumference. Good. Also, let me call this angle here, let me call it angle X. But this angle here will be in radian. And if you observe, see, if I have something like this, this is R, this is X, this is a right angle triangle, and I don't know this side. How do we get this side? It's pretty easy. How do we get this side? Let me say this side is P, and I want to find the value of P. Remember that tan X is equals to opposite over adjacent. And if I cross multiply, my P will be equal to R tan X. It means that AB here is what? R tan X. That's the way we get this stuff. R tan X. Nice. All right. Since we know this, let's start to find the areas of the shapes we have here. Remember, we have three shapes: triangle OAC, triangle OAB, and sector OAC. So what is the area? What is the area of triangle OAC? If you observe, if you have a triangle and you have an included angle theta and you have AB, this angle is between these two sides. The area here will be what? Half AB sine theta. Now look at this triangle OAC. Look at this X is an included angle between this side and this side. Therefore, I will say the area is what? Half AB, that's RR, and that's R squared, then sine theta, and my theta here is X. I believe you are getting the gist. Just follow it. There's nothing special in all this. So this is actually a proof, which is very important for us to know. So we are done with this. So let's look at the area of the sector. So let's look at area of sector OAC. See a sector for some of us that don't know. Let me draw it the way we have it here. So this is a sector. Okay, so this is X and these are the sides. So this is what we have. So what's area of sector OAC? Now, let me tell you, area of sector is what? Theta over 360 times pi r squared. So my theta is X over 360 times what? Pi r squared. But observe, since I'm dealing with radian, this 360 here, it will be replaced with 2 pi. That is radian. Therefore, this one can cancel this one. So the area of sector OAC will be equal to what? That will give me 1 over 2 x r squared. All right. Now we are done with this. The last thing for us to do is that to get the area of triangle OAB. So area of triangle OAB. And you observe this OAB is a right angle triangle. So I'm using half base times height, half base times height. And my base is R, and my height is what? R tan X. So I'll be having 1 over 2 R squared tan X. So this is what we have. Did you know something? And the thing is that, but check something out. The area of this triangle, the area of triangle OAC would definitely be less than the area of what? The area of sector OAC, and that one will definitely be less than the area of triangle OAB. Surely to be less than it. Just like you can see that this triangle is inside the sector and the sector is inside the triangle. So that is it. So let's go. So it means that we are having half r square sine what? Sine x. So it could be less than, I could apply this actually, xr square over 2. That is for this one, xr square over 2. Then less than or equal to the third one, which is half r square tan x. And if you observe what I'm having here, you see that I can divide through by these two, and also I can divide through by what? R square. Then I'll be having this sine x less than or equal to x less than or equal to tan x. Now, if you see, remember that this tan x, I can rewrite it as this. I can rewrite tan x as sine x over cos x. So I'll replace that. So I'll just, so this is my tan x now. So the next thing is for us to divide through by sine x. Divide through by sine x, what will I have? I'll have 1 less than or equal to x over sine x and less than or equal to 1 over cos x. Alright. So from here, what will I do? Pretty easy. So after dividing through by what? After dividing through by sine x. Now the next step for you is to what? After dividing through, the next thing for us is to apply the limits. So if I apply the limits where x tends to 0 for 1, less than or equal to the limit where x tends to 0 for x over sine x, where we apply the limit x tends to 0 for 1 over cos x. And what will this one give me? This will give me 1 less than or equal to, this will give me what? Actually, I could not know the answer yet. X over sine x, and also this will give me what? The limit as x tends to 0. You remember that cos 0, if I put 0 here, cos 0 is 1, 1 over 1 is 1. And remember, by squeeze principle, in the previous video, we already know that what? By squeeze principle, then the limit of x over the limit as x tends to 0 of x over sine x is equal to 1. Also, if I invert both sides, you also see that the limit as x tends to 0 of sine x over x will be also equal to what? 1. So that is what I'm trying to prove by trigonometry. I could prove this by all other methods, but since we are dealing with trigonometry, that's why I'm using a trigonometric proof. So let's go. So let me summarize all other identities you are going to need under limits of trigonometric functions. So alright, so let's go. So take note of these identities. And we have, if I have the limit of x tends to 0, sine x over x is equal to 1. The limit as x tends to 0, x over sine x is equal to 1. But what of if I have the limit as x tends to 0, sine kx over kx? Since what you are having here are the same, the answer is still 1. Also, similarly, if I invert it as x tends to 0, kx over sine x is also equal to what? Kx over sine kx is also equal to 1. What of if I have limit as x tends to 0, tan x over x is equals to what? Is equals to 1. And also limit as x tends to 0, tan kx over kx is also equal to what? 1. So that's it. So that's that for that. You can see that what this basically works for sine and tangent. So this one, take note that if I invert this, s over tan x is 1. Limit as x tends to 0. If I invert this one also, limit as x tends to 0, kx over tan x, my answer is still equal to 1. So that is it by limit of trigonometric what function. So since we've known this identity, so let's quickly look at practice problem. How do we apply this when solving problem? So let's see. Let's look at this basic problem. If I have the first question here, if I have the limit as x tends to 0 of 5x over sine 3x, what do I do? If you observe, you see that this number here and this number here aren't the same. So I can't apply that identity. So I can bring out this 5 out of the limit by property of limit. So I'll have x over sine 3x. Also, did you know that it is possible for me to put 3 here and in turn divide by 3 here? Because if this 3 cancel this 3, I'll still be having what I have. So therefore, remember that the limit, this limit here, where x tends to 0 of 3x over sine 3x. Why am I using 3 here? Because there's 3x here already. So this will give me 1. Therefore, my answer here is 5 over 3 times 1, and my answer is 5 over 3. Next question. If I have, okay, let's go stronger. If I have the limit as x tends to pi of tan x over sine 2x, what do I do from here? Well, you can see that these are different entities entirely, sine and tangent. So what can I do from here? Do you remember that tan x is the same thing as sine x over cos x? That's tan for us. Then this is what? 1 over. Do you remember this identity? I'll be summarizing the identity I'm using here. So we'll use the opportunity to learn them. And for some of us that have known it before, it will be as a division. That tan x is equals to sine x over cos x. Also, another identity is that sine 2x is what? 2 sine x cos x. 2 sine x cos x. So let's go. This will give me 2 sine x cos x. Therefore, we proceed to cancel out this. Sine x will cancel out sine x. So this will give me the limit as x tends to pi. You see this 2 here, I can move it outside. Then I have 1 all over cos square x. And check it out. If I substitute pi, what's cos pi? In other words, what's cos 180? 1 over cos square 180, or I can say cos 180 square. That's if I put my x to be pi. What's cos 180? That will give me negative 1. Okay? And negative 1 all square is given 1 over 2, then negative 1 all square. And negative 1 all square is just 1, so my answer is 1 over 2. Another question. You can jot the identity, please. Another question. Okay, let's see. What if we have the limit as x tends to 0, 4x minus sine 2x all over 7x plus sine 2x. Okay, observe, we can't use squeeze principle here because that one only work for when you have just one trig term. But here, there are more than one, so we can't use it here. So what do we do from here? Observe, what do you think we can do? Pause the video and give it a try. Nothing I could do, okay? Let me see. See the way I'm going to attack the question. Divide through by x. If I divide through by x, I'll have 4x divided by x, and that will give me 4. Minus, I have sine 2x divided by x all over. This will give me 7 minus sine 2x divided by x. All right. Also, do you know that I can actually do something like this? It is possible for me to say I have limit x tends to 0, 4 minus. This I can write it as 2 sine 2x divided by 2x. Why am I doing this? If this one can cancel this one, I'll still return back to what I have. So we really need to boost our IQ here. I'm putting these two so that this and this will be equal, so I can apply my identity, just like I've learned in this video. 7 minus. Also, I'll put my 2 here, 2 sine 2x, then all over 2x. So if I apply my limits all through, I'll be having the limit as what? As x tends to 0 of 4 minus 2 times the limit as x tends to 0 of sine 2x all over 2x all over the limit as x tends to 0 of 7 minus 2 times the limit as x tends to 0 of sine 2x over 2x. Do justice to that. So let's go. This will give me 4 minus, remember this is 1, I'll have 2, 7 minus 2, and that will give me what? 2 over 5. That's 2 over 5. Oh, there's a mistake here actually. This is positive, this is positive, this is positive, and this is positive. I'm sorry about that. So this will give me 2 over 9. This will give me 2 over 9. Alright, so this is correct. This will give me 2 over 9. Alright. So let's see another problem. Okay. Let's see. What if you have a question like this? The limit as x tends to pi over 2 cos x plus sine 2x all over cos x minus sine 2x. So this is what we have. So what do we do here? We really need to understand trig identity a lot. So I'll solve this by saying the limit as x tends to pi over 2. You will notice that this sine 2x, recall that sine 2x is equal to now 2 sine x cos x. So I'll have 2 sine x cos x all over cos x minus 2 sine x cos x. Observe that cos x is common, so I'll say the limit as x tends to pi over 2. Cos x is common, I have 1 plus 2 sine x all over cos x is common, 1 minus 2 sine x. So this takes care of this. Now, if I substitute the pi over 2 there, what will I have? I should be having 1 plus 2 sine pi over 2 1 minus 2 sine pi over 2. And check it out. What's pi over 2? That's 90 degrees. Sine 90 is 1. 1 minus 2 times 1. And that will give me 3 over minus 1. And my answer is equals to minus 3. That's as simple as that. Okay. Let's look at another problem. If I ask you to evaluate L equal to the limit as x tends to 0, square root of 1 minus cos x over x. So what do we do here? You can attempt the problem, test your ability. Alright. So when you are done testing, do you remember that recall, if I substitute 0, I'll be having 0 over 0. So you need to find a way to manipulate this problem, which means that I can rewrite cos x. Okay, let me remind you from here. Do you remember that cos 2x is the same thing as 1 minus 2 sine square x. So observe that I want to get the identity for cos x. It means that if I just try to divide these angles by 2, I'll be having cos x equal 1 minus 2 sine square x over 2. That is how you can obtain one identity from the other. So this is it. Cos x equal 1 minus or 2 sine square x over 2. We already know this already. Then we obtain this. So I'll just use that. So that will equal to what? Limit x tends to 0. Then square root of what? 1 minus, what is your cos x? 1 minus 2 sine squared x over 2. Then all over x. And I have the limit. That x equals to the limit as x tends to 0. This will give me what? Square root of, observe, 1 minus 1 plus 2 sine x over 2 all over x. So this will give me the limit as x tends to 0. 1 minus 1, that will be gone. So I have square root of 2 sine squared x over 2, then all over x. Okay, from here, if I cancel out the square, if I separate it, I'll be having limit. What do I mean by separating? This one will give me square root of 2. And if I put square root on something like this, sine squared x over 2, this square will take care of the square root to give you sine x over 2. Then you have all over x. I can pull this out to be square root of 2 times the limit where x tends to 0 sine x over 2 all over x. Now, what do I do from here? Do you know that? Well, find a way to make this one over 2. So observe that if I put this one over 2, I can multiply by 2. So they will cancel out. And these 2 that I've multiplied by, I can pull it out to be square root of 2 over 2. Limit x tends to 0 sine x over 2 all over x over 2. And what's my answer here? Square root of 2 over 2, because this one is equal to what? 1. So that's how we evaluate limits. So let's solve one more problem. What if you have the limit as x tends to pi, tan of sine x all over sine x. How do we evaluate these limits? Well, it could be so difficult like this. Yeah, it could be so difficult like this. But do you remember that our identity was if I have the limit where x tends to 0, tan x over x, then my answer will be 1. But here is not tending to 0. So I can't apply the identity that way. If I do that, then my approach will be wrong. So what will I do from here? It's very easy. I can do some substitution that I can substitute and say, let's let y be equal to sine x. If my y is equal to sine x, see, as x tends to pi, y will tend to 0. Therefore, because see, if x tends to pi, sine 180 is 0, then my y will tend to 0. Therefore, I'm having the limit as y tends to 0 tan y over y. And tell me, what is tan y over y? Tan y over y will be what? 1. Nice approach. So that is it. So lastly, the last problem for today is this. The last problem for today is this. If I have the limit as x tends to 0 of cosec x minus cos x all over x. So let's see. To solve this type of problem, just reduce the limits that you have. Just reduce the trick you are having here. Cosec is 1 over sine x. Cot is 1 over tan x or cos x over sine x. That's cot. All over x. So from here, I'll be having limits as x tends to 0. Our LCM at the numerator is sine x. So I have 1 minus cos x. Remember, they are having the same denominator. Just pick one and add the powers together. Then all over x. So I have the limits as x tends to 0. 1 minus cos x all over x sine x. It's possible for this to come down with it. So I have x sine x. Okay, look at what I'm having here. What can I do? Well, what can we do? Okay, let me work this way. Limit at x tends to 0. Let me keep this 1 over x separate. Then I have 1 minus cos x over sine x. So from here, let me multiply. Let me rationalize this function. How am I knowing what to do? The thing is that once I'm saying trig like this, I'll have to reduce it to something like this. Then after that, I will simplify. After simplifying, if I see that it will not still make sense if I substitute x, I will try to manipulate algebraically. That is, looking at this one, I'll know that, okay, let me rationalize this numerator. And let me see. So rationalize 1 plus cos x, 1 plus cos x. So what will I have from here? That will give me limit as x tends to 0 of 1 over x times. This will give me 1 minus cos square x for the numerator. For the denominator, you have sine x, then 1 plus cos x. If you remember, this is difference of two squares, 1 minus cos x. So I can write this as limit as x tends to 0, 1 over x, then 1 minus cos x, 1 plus cos x, 1 over sine x, 1 plus cos x. Therefore, this will cancel this. If it's cancelled out, what will be the next step? That will give me the limit as x tends to 0. So I have 1 over x here, then 1 minus okay, 1 minus cos x, right? Oh, please let me check my working. So 1 minus cosine. Oh, there will be a mistake somewhere, please. Sorry, pardon. I'll still be turning back. Okay, so I'm going to do from here. See, remember that sin square x plus cos square x is equal to 1. So sin square x will be equal to 1 minus cos square x. So this 1 minus cos square x, I'll replace it with what? Sin square x. So I'll be having the limit as x tends to 0, 1 over x times. This will give me sin squared x over sin x 1 plus cos x. So doing this, I'll know that this sin x here will cancel one of these. So I'll be left with the limit as x tends to 0. So I can, this sin x that is remaining here, I can write it like this: sin x, then I have over x, then 1 over. And remember property of limit. I can separate this limit for both of them. I can separate the limits for both of them. So this will give me 1. We already know. Then times this one, cos 0 is 1. 1 plus 1 is 2. So I have 1 all over 2. And my answer here is what? 1 over 2. So that's the end of the video. Please like, comment, share, and subscribe to this channel. So when I release any vital content, you'll be notified. It does not consume data and it consumes nothing. Click on the subscribe button and notification bell. Now take this as a task and comment your answer. Okay, solve this problem. Limit x tends to 0 cos 3x minus cos x all over x squared. Thanks for watching.